remember what we're doing is we're packing our toolkit so that we know what it is we need to address understanding astronomy. So don't despair. Rather than trying to summarize all the disparate things we talked about, let me do an example of an application to actual astronomy of what we learned about that might clarify some things. So let's talk about the sun. We said that the sun radiates its heat. Let's see what all our various results tell us about solar radiation. So we can measure the brightness of sunlight on Earth in watts per meter squared. How do you do that? Well, put out a meter squared of detector and measure how much sunlight hits it. Put out a meter squared of something very dark that absorbs all the sunlight. Measure how much energy that thing receives. And you find the number is called the solar constant, and it is 1,361 watts per meter squared. So a meter squared of sunlight will run a very small hairdryer or light 10 incandescent light bulbs. So we know the intensity of solar radiation in the vicinity of Earth. Now, we know how far the sun is. The sun is 1 astronomical unit, or 150 million kilometers away. And so if we know how bright it looks and we know how far it is, we know that we can compute its luminosity. Remember, we had that B, the brightness, is the luminosity divided by the area of the big ball, whose radius in this case is the distance to the sun, or 1 astronomical unit. And so we can solve this. We know the brightness, we measured it. We know the distance. We can write an expression for the luminosity, and it's 4 pi times the distance to the sun squared times the brightness of the sun. And so we put in the numbers. This is 4 pi times 1.5, I'm rounding, times 10 to the 11 meter squared times 1361. And we evaluate the calculation, and you find that the sun is a very bright light bulb indeed. It has a luminosity of 3.8 times 10 to the 26 watts. That's a lot of energy lost by the sun. Now, we can measure the radius of the sun. Since we know the distance, we can make a small angle calculation. We measure the angular size of the sun in the sky, and we find that the radius of the sun is 6.96 times 10 to the 8th meter. That's about 700,000 kilometers. And from this, we can figure out something else, because what we know now is that, think of the sun as a ball. Every square meter of the ball is radiating light to the outside. You count how many square meters there are on the surface of a ball. That would be 4 pi times the radius of the sun squared. If I multiply that by the flux, the amount of power in watts emitted by each square meter, this should equal L. Since I know the radius of the sun and the luminosity, the total amount of energy that's being emitted, I can figure out the flux that each square meter emits. Now, the luminosity, as I said, is the area of the sun times the flux, and so I could compute the flux. The nicest way to do this is to use a scaling relation as usual. So the scaling relation is going to be that I have that F, which is L over 4 pi times the radius of the sun squared, and I have that B is L over 4 pi times the distance to the sun squared. I can cancel everything around, find that L is B times the distance to the sun divided by the radius of the sun squared. And this relates, again, a flux to a flux through a dimensionless quantity. I recommend this method of computing, and this is 150 million, this is 700,000. That's a big factor. Every square meter of the sun produces 6.3 times 10 to the 7 watts. A square meter of sun produces 63 megawatts of light emitted out towards the universe. That's a large number, but we can go further. We have the flux, and we know the Stefan-Boltzmann law. We know that the flux is also equal to sigma t to the 4th, since the sun emits approximately as a black body. It's dense enough. And so, since we know the flux, we can compute the temperature, and we can actually find the temperature of the part of the sun that we see. It's called the photosphere. It's somewhere outside on the surface of the sun. And we find that the temperature is the fourth root of F divided by sigma. The temperature of the radiating surface of the sun, of the photosphere, is about 5800 Kelvin. I can use Wien's law, because I know the temperature, to figure out the wavelength of maximum emission for the sun, the wavelength at which the sun emits more light than anything else. I take Wien's constant, 0.0029 meters is the value of Wien's constant. I divide by the temperature of the sun, and I find that the sun produces more light than any other frequency at a wavelength of 503 nanometers. And if you look up the table, this is somewhere between the red and the blue, and indeed, it is green. But Ronan, you tell me, every kindergartner knows the sun is yellow. Yes, but not really. Every kindergartner knows the sun appears yellow. Why that is consistent with the maximum emission being green, we'll see in the next clip. In the meantime, go and catch your breath. We have gone through many, many different topics here. We have a whole grocery list of new ideas and new concepts to digest and to learn how to use, and we'll start applying those very soon.